Okay, so today is one of my absolute favorite set of notes. So you guys have done candidates test, first derivative test, second derivative test. You've looked at increasing and decreasing based on the first derivative. You looked at concavity based on the second derivative. Today is where it all comes together into what we call curve sketching. You kind of have done a little bit of this on your own with some of the worksheets you've done over the past couple of days, but today we're taking a function and basically breaking it down into all of its components. Why? Well, you have to remember, guys, so what came first, the calculator or calculus? Definitely not the first, okay? So basically, when we had these functions, people needed to come up with a way of figuring out what exactly they looked like without plugging them into a calculator. That wasn't a thing. Also, we could just plug out a bunch of numbers, but that takes a lot of time. It's super tedious. So what else could we do? Well, we look at all the properties of our functions, and then we can pull those things together and create, basically a function from scratch. It's kind of cool. Just pay attention. Okay, so what I want you to do, like normal, read these two questions. These are two separate questions. I want you to give them a try on your own, pause it, try it out, sketch it, and then see if you get something similar to what I'm going to get. Now, because there are so many different, like this isn't a set function, this is just a bunch of properties about two different functions. So there are some opportunities where your answer might be a little bit different than mine, but as long as you meet all of these criteria here, and on the other one, as long as you meet all of this criteria here, your answer should still be correct. Okay, so when I do these, I kind of like to write notes off to the side. So f of 2 is equal to f of 4, which is equal to 0. Okay, those are what looks like two x-intercepts. Okay, so I have my x-intercepts. I have one of them at 2, 0, and the other one at 4, 0. Okay, so then f of 3 is defined. Okay, that means there's a point at f3. I'm not sure since they only gave me an x coordinate here, I don't know what the y coordinate is, but that's fine. I can put it wherever. F prime of x is less than 0, or f prime of x is negative if x is less than 3. So when the derivative is negative, that tells us that f is decreasing. So a function is decreasing when x is less than 3. Okay? F prime of 3 does not exist. Okay, so I knew that I have a point at 3, but the derivative does not exist. So when I see that, it tells me it can't be an asymptote because this is defined. But what it could tell me is that there's maybe a sharp turn or a cusp right here. So I'm going to go ahead and write possibly a cusp on that one. Okay. And then f prime of x is positive if x is greater than 3. So that means f is increasing. Okay, so before 3, my function is decreasing, but after 3, my function is increasing. Cool. Okay, the last bit, f double prime of x is less than 0, so my second derivative is negative when x is not equal to 3. So basically everywhere except at 3, my second derivative is negative, which means my function is concave down. Okay, so let's try to put all of this stuff together. Just take it one little piece at a time. So I have my two x-intercepts. So I've got 1, 2, 3, 4. I've got a point here. I've got a point here. I know that f of 3 is defined. I'm not really sure where to put that yet. I'm going to kind of hold off until I know for sure what's happening. Let's see. So my function is decreasing up until 3, but then it's increasing after 3, and it's concave down. So it's going to be decreasing on this side, increasing on this side, but always concave down. So what I'm going to do, I'm just going to assign this as my y coordinate for 3. I don't have a specific answer because they didn't really specify. And when we grade this kind of stuff, we look to make sure that you satisfy all of these requirements, but you can have some variation. So because my function is decreasing and concave down, I'm going to go this way, over here, and then increasing concave down on that side. So that's a potential option for my graph. It doesn't have to look exactly like this. We could, if we wanted to. F of 3 is defined, but the derivative does not exist, I don't actually know that it's a continuous function. Another option would be to have a hole or removable discontinuity right here. If I wanted to, a potential option would be to, let me take away this little guy right here. I could have an open circle here, but then 3 could be defined, you know, pretty much anywhere above or below. It could be like that. Okay, that's another alternative. Both of those would be correct. Okay, if I had some indication that my function was continuous, then I would have to go with my first option, which was to put this guy, put this thing, you know, right here, basically. But you know, they don't specify, so both answers would be perfectly fine. Okay, let's look at the next one. So, okay, we start off with f of 2 is equal to f of 4 is equal to 0. So I'm going to go ahead and just go 1, 2, 3, 4. Put those there. Okay. F prime of x is positive if f is less than 3. So that means f is increasing when x is less than 3. And then f prime of 3 does not exist. So the derivative does not exist, okay, which it didn't over here. It could be another cusp. Over here specifically, they said that f of 3 was defined. They don't specify that over here, so it could be a cusp or maybe an asymptote. Okay, one of those two. Let's see, f prime of x is less than 0, so the derivative is negative if x is greater than 3. So now f is decreasing. So it was increasing before 3, decreasing after 3. And then my second derivative is positive, which means f is concave up everywhere except at 3. So there's really two options I could see here, mainly because of these two things. Well, I guess I say two options. There's lots of different ways to draw this, but one way that I would easily see is just to go ahead and put an asymptote here at 3. My function is concave up and then increasing on this side. So I could go here like that, and then it's decreasing but still concave up after 3. And I'm still going through my x-intercept. So that's one option. Another option, let me move this over a little bit here. Another option is to have the two x-intercepts again, but let's put an open circle at 3 to where it's not, I mean, we only know that the derivative does not exist. We don't actually know that the function itself does not exist. So I could have this right here, and then just like we did earlier, I could either fill this in, maybe, or I could not have it filled in. It doesn't say that the function is continuous. I just know that the derivative does not exist there. So, so for this one, you could have, you know, the whole filled in, or wait for it, or I could not have it filled in. Option 1, option 2. 1, 2. I mean, either one, or lots of other alternatives from that. Okay, so this is how we would draw these if we just had some basic descriptions about the graph. So now I'm going to give you an actual function, and we're going, oh no, I forgot that I had this page. My bad. So let's see. Oh, this is the exact same thing, but on an actual pretty graph. That would have been cool if I had recognized that before I made it. But you know what? It's all good. It's fine. We're just going to skip on over those. No problem. Okay, so analyze and sketch the graph of 2 times x squared minus 9 over x squared minus 4. Okay, I'm actually going to take this graph and I'm going to shrink it, set it off to the side for a second. I'm going to come back to that. I feel like I have a lot of work to do before I get close to touching the graph. So with this video, I'm going to have one example on here that I'm going to work all the way through start to finish. Okay, there are 3 more examples after that I will post on Canvas, the filled in version of those examples, but I really feel like just me walking you through one of them is probably sufficient enough. If you have questions, most of these are from the textbook, and I think you can get videos from them. that explain it. And as of course, as always, you can go to Prof. Rob Bob and Khan Academy. But hopefully this gives you a pretty good idea of what we're doing. So when I need to analyze and sketch the graph, I want to first go back to everything that I know before I walked into my calculus classroom. Okay, so what are all of the things that we've talked about well before this class? Like Algebra 1, Algebra 2, Pre-Cal. What have we talked about? The most basic things I can think of are my x and y intercepts. I'm gonna start with that. So my x-intercepts is where my y value is equal to 0. So I'm going to set my entire function equal to 0, or really since it's a fraction or a rational function, I'm just going to set the numerator. So I'm going to say 0 equals 2 x squared minus 9. Okay, so 0 equals 2 x minus 3 x plus 3. So then x equals plus and minus 3. So my actual intercepts would be 3, 0, and negative 3. 0. Okay, if I wanted to, I could go ahead and plot those. I'm gonna plot all of this at the very end, I think. I don't know. We'll see. We'll see how I feel as I go along. Okay, y-intercept. My y-intercept is where my x value is equal to 0. So essentially I want to find what is f of 0. So that's going to be 2 times 0 squared minus 9 over 0 squared minus 4. So that's going to be 2 times negative 9 over negative 4. So what is that? Negative 18 over negative 4, so positive 9/2. Okay, so my y-intercept is going to be at the point 0, 9/2. Again, personal preference, you can plot as you go, or you can plot all of this at the end. You know, it's really just kind of up to you. I'm gonna wait and do this at the end. I'll bring the graph down with me and we'll do it at the end. Okay, so so that's my x and y intercepts. The next thing I want to look at are, let's see, we talked about this I think for the first time when you hit Algebra 2, and then I know we touched on it again in Pre-Cal, but we talked about the horizontal and vertical asymptotes. You guys remember those? So my vertical asymptotes, since I already did x up here, let's do vertical asymptotes. My vertical asymptotes are where they occur where my denominator would give me a 0. So I set my denominator equal to 0. So I'm going to say x squared minus 4 is equal to 0. So x squared equals 4, x equals plus or minus 2. So my vertical asymptotes are at x equals plus and minus 2. Okay. Well, I say horizontal asymptote. I actually prefer to call them end behavior asymptotes because they're not always horizontal. Sometimes you have a slant asymptote. I hope you guys remember the rules for your end behavior asymptotes. Remember, we have top heavy, bottom heavy, and balanced. In this case, it looks like my degrees at the top and bottom are very balanced. So if that is the case, what do we look at? We look at our leading coefficients, and our leading coefficient is going to be a 2 in the numerator and then just a 1 in the denominator. So y equals 2 is my end behavior asymptote, and I want to write a little note because they were balanced. Okay? Remember, if it was top heavy, which meant you have a higher degree on the top, you would have to do long division to find your slant asymptote, and if it was bottom heavy, it would just automatically be 0. So this is now everything that I know up to this point without any calculus knowledge. So from here, what we did in Pre-Cal and in Algebra 2, you would plot all of these things, and then you would basically just have to plug in some points and kind of have an idea of what the graphs maybe could have looked like, and then just kind of, you know, winged it from there. But luckily in the world of calculus, we have ways of making our guesses essentially a little bit more accurate by looking at where is my function increasing, where is my function decreasing, is it concave up, concave down, all that good stuff. So now let's go ahead and determine increasing and decreasing, okay? So to do that, we look at our, anyone tell me? First derivative. So I'm going to go ahead and rewrite my function down here so I don't forget what it is. F of x was equal to 2 x squared minus 9 over x squared minus 4. Okay, so to take my derivative of this lovely function, I'm going to have to use everyone's favorite, the quotient rule. The f prime of x, derivative at the top, so 2 times, let's see, 2x essentially, times the bottom, squared minus 4, minus the top, times the derivative of the bottom, so another 2x, all over the bottom squared. Okay, I'm not seeing any way to clean that up just yet, or I don't think I can simplify anything, so I'm going to go ahead and just multiply all of this out. And I'm going to have, let's see, 2 times 2x is 4x times x squared, so 4x cubed. And then that 2, the 4x times negative 4, so minus 16x. And then I'm going to have, let's see, 2 times x squared, so 2x squared times 2x, so 4x cubed. And then negative 2 times negative 9, so that's going to be positive 18 times 2x, so plus 36x. Refer back to my notes here, make sure I'm on the right page, because every now and then it does happen that I have a little snafu and I want to avoid those. And then x squared minus 4 squared. Okay, luckily I can clean this up a little bit because these two things cancel out. Those go away. Negative 16x and positive 36x gives me 20x. So my actual derivative, all simplified out, is going to be 20x over x squared minus 4. I'm glad that cleaned up a little bit better because then that'll help when I take my second derivative for concavity here in a little bit. So squared. So before, speaking of that second derivative, before I do that, while I'm at my first derivative, in order for me to determine where my function changes from increasing and decreasing and vice versa, I need to go ahead and find out where this is equal to 0 and where it would also be undefined. So where f prime of x is equal to 0, that's when I set my numerator equal to 0. So at x equals 0, that's where my derivative is equal to 0. Cool. Okay, where is f prime of x undefined? Okay, that's what this. That's going to be where my denominator is equal to 0. Well, that's basically just the square of the same denominator I had in my original function. So that's still going to be x is equal to plus and minus 2 because those are the vertical asymptotes of the original function. Okay? All right, so where my derivative is equal to 0 and undefined, what do we call these numbers right here? Anyone? Anyone? Guesses? Those are our critical numbers. Now, this one, if I plugged it in, would be a critical point after I plugged it in and found its y value. This one would not. Can anyone tell me why? Well, I'm sure you could tell me why if you were here with me right now, but the reason is because this is a vertical asymptote. It does not exist on the function, therefore it would not exist on the derivative either. Okay? So, I know that my derivative is going to change from increasing and decreasing possibly at these critical numbers, but we'll put all that in the chart here in a little bit and analyze that from there. Okay, let's go on to my second derivative. Okay, again, we need to use the quotient rule. Shouldn't be too bad. Derivative at the top is just 20, and then x squared minus 4 squared. But we are going to have to use chain rule. Daggone it. 20x times 2 x squared minus 4, 2x, all over x squared minus 4 quantity to the fourth. Before I go any further with my simplification process, I want to make sure I reduce wherever I can. I see a lot of x squared minus 4s floating around, so I'm going to take, let's see, I can take one out. I'm going to take this one out. That becomes a 3. This becomes to the first. And now I can go ahead and multiply everything else out as is. So then 20 times just one of those. So my second derivative. So 20x squared minus 80. And then minus Okay, so all of that went away. So 20x times 2 would be 40x times 2x. So then times 80x squared. Okay, so far so good. All over x squared minus 4th. Now to only the third power. I've got some 2x squared terms, so this becomes negative 60x squared minus 80 over x squared minus 4 cubed. Okay, so now to determine where my function potentially changes concavity, I need to find out where my second derivative is equal to 0 and also undefined. So, did not mean to do that. Hang on, I'm trying to scroll down here. That did not go as planned. That's okay. So, I'm going to say second derivative of x is equal to 0. Ooh, whoops. 0 at negative 60x squared minus 80. Set that equal to 0. Negative 60x squared equals 80. X squared equals 80 over negative 60. I get x squared is equal to negative 4/3. That's going to have no solution. Okay, that's going to be an imaginary root there, and so basically no real solution. So there's not a place where my second derivative is equal to 0. Is there a place where my second derivative is undefined? Why, yes, there is. The same place that my first derivative is undefined and my function itself. Again, I have this in the denominator, the x squared minus 4. So then f double prime of x undefined at vertical asymptotes. X equals plus and minus 2. Okay, so that's a lot of information. And again, we could graph all of this at once, but here's what I like to do. I'm going to put all this in a nice, pretty chart using the same kind of intervals we did with our first and second derivative tests, and then kind of just plug things in and then go from there. So the main numbers that I had that have popped up today, aside from my intercepts, okay, the intercepts, I'm going to leave those alone unless they happen to also be a critical number, okay? So my critical numbers were x equals 0, plus and minus 2. I'll just write that as 0 and negative 2 and 2. And then if I had any potential points of inflection by having a where my second derivative was equal to 0, I would also list those here in my intervals, but I don't have one here, so we don't necessarily have to worry about that. So because these are the only numbers that I have to break this whole thing up, I'm going to say I've got, okay, I'm going to make a big chart here, but I don't know that that's big enough. Boop. All right, so we're going to start from negative infinity, and it goes to negative 2. We want to talk about what's happening at negative 2. Then we're going to go from negative 2 to 0. Talk about what's happening at 0. I'm going to go from 0 to 2. And then talk about 2. And then 2 to infinity. Okay? And I'm going to talk about... Now, I've done this in different orders in the past because I'm eventually trying to get to where I'm graphing this whole thing. I'm just going to go f prime, f double prime. All the way across here, all the way across here. Some people also put in their x and y intercepts right here. You're welcome to do that. I like to not do those because sometimes kids get confused on does it change concavity or increasing, decreasing at those places? Not necessarily. It could, but it doesn't have to. So that is going to, I'm going to leave that up to you however you want to do that. This is how I'm going to work my chart, but you do you. Okay, so the things that I know so far, at negative 2, this was a vertical asymptote. Okay, so that means this was undefined here and undefined here. Okay, I also know that was the same thing at positive 2 vertical asymptote, so undefined and undefined. Now, when x was equal to 0, I believe, if I recall correctly, you scroll up for a second here, when x was equal to 0, not only is that my y-intercept, but that was where my derivative was equal to 0. Okay, so because that's my y-intercept, I can go ahead and write 9/2. I know the coordinates of that point, but my derivative was equal to 0 there. So that tells me it's possibly a relative min or a max. I could use the second derivative test. Since I know I need to go ahead and find out increasing, decreasing, all that good stuff, I'm just going to hold off and use that to help me determine if my function is, if that's a relative min or a relative max at that point. So, okay, where do we start? My second derivative is closest to me, so let's just go from there. So f double prime, let's look at f double prime at, say, -3. Okay, so f double prime of -3. So that means I'm going to plug -3 into my second derivative here. Okay, well, the nice thing is, basically, no matter what number I plug in here, so this term would always be a positive because you're squaring it, right? But because you're squaring it and then turning around and multiplying by a negative number, this entire term right here, just from here to here, that's a negative. And then you subtract further, so that whole top piece, no matter what you plug into your numerator, everything up here is going to be a negative. Okay, that's going to be very handy. So we have a negative in the numerator. And then let's check the denominator. So x squared minus 4, if I plug in a -3, well, -3 squared is 9, minus 4 is +5, cubed is still positive. So negative divided by positive is going to be a negative. Okay, so that's what's happening at that interval. Okay, let's look at f double prime of -1. F double prime of -1. So when I plug in a -1 up top, again, always have a negative. You're always going to have a negative. So I have a negative up top. -1 squared is just 1 minus 4, so -3. A negative number cubed is still a negative. So I have a negative divided by a negative, so that's positive. So this is positive. Okay. If I plugged in a 0, well, let's do that. Why not? Oh, I have a negative up top. I have a negative on the bottom, it looks like. So negative over negative, yet again, is a positive. Oh, because I've already done that, I actually already know from the second derivative test that my critical number, which means my first derivative was equal to 0, okay, but my second derivative is positive. That means my graph is concave up, which makes this point right here a relative min. You know, it's kind of hard to see because the handwriting is a little smudged, but this point right here is going to be a relative minimum. Cool. All right, let's keep going. I need to look at f double prime of +1. Negative up top over a negative, so that's going to be a positive. F double prime of 3 is going to be negative up top over a positive, so this is going to be negative. So now I can determine concavity. So I'm going to leave a little space because I also need to write out increasing and decreasing, but because I've already done the second derivative, I can determine that my function is concave down, doesn't exist here, concave up, still concave up, and then concave down. Now, here's a quick question. Notice my concavity changed from concave down to concave up, and then stayed concave up, and then changed back to concave down. Because my concavity changes over an asymptote, remember, this is not a point of inflection. The concavity changes, but it is not a point of inflection. Okay, a point of inflection would only occur if you had an actual point that existed on the function. So like here, this point still exists on my function, but see how my concavity does not change? So it's not a point of inflection. It's just a relative minimum. Okay. All right, now let's look at our first derivative. So I need to repeat the process that I did on my second derivative, but in my first derivative. So I'm going to plug in, f prime of 3, f prime of 1, and you don't have to use the same, -3 and -1. You don't have to use the exact same numbers I did. I just go with what I feel like is the simplest. F prime of 1, f prime of 3. And I'm going to just tell you that I've done the math here. Again, I do the whole, look for the positives and negatives up top and bottom. And actually 20x over x squared minus 4 quantity squared. Remember, this was my first derivative, okay? Basically, no matter what number you plug into the denominator, you're always going to get a positive value because you're squaring in. So you really just need to look at the numerator. So that tells me that whenever I plug in a negative into the numerator, I'm going to get a negative. So I'm going to do the same thing here. But then I would have positive over here. Check my notes, make sure that that makes sense. Negative, positive, yep. And then also, the nice thing is that also confirms that at 0, my derivative changed from negative to positive, again confirming that this number was a relative, or this point is a relative minimum. Okay, so because my derivative is negative, that means my function is decreasing here and here, but now it's going to be increasing and then again increasing. Okay, so I've got this entire chart filled out, and now you're like, okay, what do we do with that? Let me grab that graph real quick, bring that back down here, and let's put all of this stuff together, little bit at a time. Here we go. Make that a little bigger. All right. So we had our vertical asymptotes. Let me see if I can get that. Yeah, it'll fit. My vertical asymptotes were at -2, 1, 2, and +2. My end behavior asymptote was at y equals 2. Okay, and then I also had my x-intercepts, I believe, were at 3 and -3, so x-intercept here, x-intercept here, and then my y-intercept was at 0, 9/2. 9/2 is like, what, 4.5, so let's see, 1, 2, 3, 4.5. So that's my y-intercept. Okay, this is what we are allowed to graph, or what we know based off of Algebra 2 and pre-cal knowledge. From here, you would have to plug in numbers to figure out what's happening everywhere else, but welcome to calculus. We've done all of this lovely work to figure out exactly what our graph is doing. So starting from the left, I know from -infinity to -2, my graph is decreasing and concave down. Okay, and I know it's got to go through this point right here. So it's going to go decreasing, but concave down, never crossing the vertical asymptote right here. Now, this horizontal asymptote, okay, I'm going to assume it doesn't cross it. There is a possibility that it could. For right now, we're just going to pretend that it doesn't, okay? We would have to check a little bit more than that, and that's not quite, we're not there yet. Okay, actually, if it did, it would probably like go up and back down, which means your graph would increase and decrease. So you'd have more critical numbers here, like a relative min or max. So boom, we're good there. Okay, vertical asymptote -2. Let's look at this window of opportunity. Between -2 and 0, my function is decreasing and concave up, but I know it's got to go through this point right here. So I'm going to go decreasing, but concave up. I know after this, I've got 0 to 9/2, from 0 to 2, for this interval right here, my function is increasing and still concave up. So now I'm going to go increasing and concave up. Okay, vertical asymptote, got that. 2 to infinity, my function is increasing but concave down and still has to go through my x-coordinate here, or x-intercept. So it's going to look like that. Boom, done. All of that lovely work, and it created this beautiful rational function. Okay, on the next slide, I have the book's version. Oh, look, they got the same thing we did. How wonderful. They do their chart in a slightly different way. Basically, it's just, sideways compared to what I have. I have zero preference on how you want to draw your table. If you prefer this way, go with that. If you prefer the way I did it, go with that. Or if you have your own special way, do that as well. Okay, so that is how you sketch a curve, literally start to finish, looking at all of the components: x-intercepts, y-intercepts, vertical asymptotes, end-behavior asymptotes, increasing, decreasing, concave up, concave down, relative mins, relative maxes, all that good stuff. There are 3 more examples on this slide. Not on this video, okay? I'm going to end the video here, but if you would like to graph the other 3, okay, they're on Canvas. I will post both a blank version of this on Canvas and then a filled in version of this on Canvas, so that way you can have, you can see what the graphs are, or what the questions are, and try them on your own if you want to, and then you can check your answers afterwards. But as always, if you have questions, your book is a great resource. Khan Academy, Prof. Rob Bob. Good luck, have fun, enjoy curve sketching, one of my absolute favorites.